Okay, gang, hello. Again, technical difficulties recording the first video. I'm going to blame it on my dog Moose. I can't believe I would create a problem, but somehow I didn't get it uploaded to YouTube. And so I'm going to kind of go through our discussion earlier today quickly. To kind of summarize what we did. And again, if I leave something out in the second one that I talked about and you want to have further discussions, feel free to give me a call back or contact me. We'll get together on video chat if we need to. So here we go. We started out today talking about the finding the sampling distribution for a sample proportion. And what I'm talking about is, think back to the red bucket, the bucket with the red and blue chips. Taking a sample of 20 and finding the proportion of red ones in the sample. That's what we're talking about. We calculate a proportion of red chips in the bucket, and that's what we're creating a distribution of. Every time we take one of those samples, that's a new dot on the plot. And as we've talked about in class before we left, the sampling distribution of sample proportions is all of the possible samples of a certain size from the population. And so if you've got a large population, that's a lot of samples, a lot of samples. We can never, ever take that many samples. So practically what we do is we take several samples, 25, 50, 100 samples, we plot that, and from that data we make decisions about what the population parameters are. Those things that we calculate from those samples are the statistics, and today we're talking about the statistic p-hat, which is an estimator of the population parameter, the proportion. So when we have that sampling distribution, we talked about this in the video the other day, we can calculate the mean of p-hat, and it's equal to p. The standard deviation of p-hat is equal to the square root of p times 1 minus p over n if the 10% condition is met. In other words, if the sample size is less than 10% of the population. In other words, if the sample size is small, very small compared to the population, then these two things are true. If the sample size is large compared to the population, we can't depend on these things being true. It turns out that the mean of all of the proportion samples that we take is just equal to the population parameter, whatever that is. And think back to our bucket of red and blue chips. If we took enough samples and we added up the proportion in each one of those samples and we calculated an average, then that number we would expect to be right on the population proportion, which was 0.5. There were 50% red chips in the bucket. Now, the standard deviation is a different matter. We have to calculate the p, which is the probability of success or the proportion of success. 1 minus p is the probability or proportion of failure. N, however, that's the thing that changes. And it's easy to see from this equation that large sample size is better, because as n goes up, the standard deviation goes down. And as an estimator, remember the targets that we put up in class the other day, an estimator, we want a tight grouping. We want all of the dots to be close together. That's low variability. And so an estimator for a population parameter needs to be unbiased, and it needs to have low variability. That's the ideal characteristic. And so to try to drive that variability down, we increase the sample size n. And so you might ask the question, how large does n need to be? Well, it's like I've always said in class, it just needs to be large enough. Sometimes large enough is 25, sometimes it's 50, sometimes it's 100. It just really depends on the context. Fortunately, in this course, N will most likely be given to you, or you'll be given some notion of what N should be. But anyway, to drive that standard deviation down, we want to increase sample size. Always keep that relationship in your mind. Now, we've talked about the center and the spread. What do we know about the shape of the sampling distribution? Well, the shape of the distribution, we can tell if these two conditions are met, that it's normally distributed. In other words, if the number of failures, N times P, the number of successes, that's the number of successes. If that number is greater than 10, and the number of failures, I see I left off a parentheses here. If the number of failures, which is the sample size times 1 minus P, if that number is greater than 10, then our sampling distribution, the shape of our sampling distribution is going to be normally distributed. And man, that's really, really handy for us to be able to make that assumption. But we got to check to make sure N times P is greater than 10 and N times 1 minus P is also greater than 10. So we'll see in a minute. I'm going to pull up an applet that will help us kind of see how that works. Those of you who were on the video earlier, this is the candy machine, and hopefully I'll get it better this time than I did the last time. We'll see. Let's see. I want to pull up this guy.
Are you talking to somebody?
Yeah. I want to pull up this guy right here. And, oops, I want to share this screen now. Okay, so hopefully you see the candy machine, and I'll reset some things here from our previous discussion. Okay, let's clear everything out. Okay, so here's a candy machine. It has candies that are orange, yellow, and red, and we want to find the probability that a particular one is orange, and the proportion of orange ones in the machine is 0.3. We can set that to any number. We can make it 0.4 or 0.5, whatever. But 0.3 works really well for us, okay? And so when I push the draw the samples button, you can see we're turning the crank, and red and yellow ones go into this bin, orange ones go into this bin, and the p hat is 0.32. The percentage or the proportion of orange ones in that sample of 25 is 0.32, and here's our dot. So if I take another sample, I'm going to create another p hat. Every time I take a sample, that's a p hat. That's a dot on my dot plot here. And so let's go ahead and take 8 more, and to give us a total of 10, and we'll start to see our sampling distribution take shape. Now, this is not the sampling distribution because I'm not taking every possible sample of size 25 from the distribution. I'm just taking a few. Here in just a second, we'll have 10. And you'll see 8 more dots show up here, and we'll begin to take a look. But what we expect to see is that the center of this shape is going to be around 0.3. And you can kind of see I've added the normal approximation curve here. And so all the dots are falling inside the shaded region. And the peak of the bell curve is right on top of 0.3. That's what we expect. And so with the 10 dots we've got now, it's kind of, if I didn't know what to expect, I'd kind of look at that and say, I don't know what to think. Well, let's take 10 more. And to speed things up, I'll turn off the animation. You've seen that happen. So now I'm just going to draw the 10 more. So now I've got a total of 20 samples. And I'm beginning to see a little shape, but you know what? It's kind of funny right there um, in the middle. So let's take 10 more. Now we're beginning to fill in the middle, and things are looking a little better. Oops, I've got one odd one out here. That's okay. So now I've got 30 samples total. Let's make it a total of 50. And now I look at that and I'm beginning to see that normal shape. My dot plot is much better lining up with that bell curve. So let's make it a total of 100 samples and then we'll see what we got. Look at there. That's almost a perfect one in terms of real life. It doesn't get much better than that. We've got a few values that are above the curve, a few that are below, but in general, it follows that pattern pretty doggone well. So now the thing is, we want to talk about what is an unusual value. We see this thing sitting right out here. And if you think back to the empirical rule, an unusual value, we can talk about something being 1, 2, or 3 standard deviations away from the mean. And normally we'll pick 2 standard deviations away from the mean as the example. As something that's very unusual. So what would be 2 standard what value, which of these values here would be 2 standard deviations away from the mean? Well, we can calculate that. We know that P is 0.3. So 1 minus P is 0.7. So we can simply just put that in the calculator here. We'll take the square root of 0.3 times 0.7, and we'll divide that by the sample size of 25, and that gives us a standard deviation of 0.09. I'm going to round that up to, well, no, I'll just call it 0.09 for now. We'll use 0.09. And if you calculate 2 standard deviations away from that, that would be 0.3 minus 2 times 0.09 is 0.12, and 0.3 plus 2 times, oops, 0.3 plus 2 times 0.09 would be 0.48. So anything that is less than 0.12 or greater than 0.48, we would look at that and say that's kind of an unusual value. Well, the cool thing about this thing is that we can check that. So I'm going to look for the number of values greater than 0.48. And in our sample of 100, 4 of them fell outside that line. That doesn't mean that something's wrong with those values. It's just that they're really, really unusual. And if I took one sample and one sample only, and I found this guy here, I would say, you know what, that makes me wonder if the real population proportion is 0.3. I don't wonder that now because I know the population proportion is 0.3. But if I didn't know what it was, and I got a value out here in this right-hand tail greater than 2 standard deviations, I would say, man, based on our simulations here, that's a very unusual number, and it makes me wonder, makes me be skeptical. In stats, you never say, oh, I know the population's not, or the population parameter is not 0.3. We just say we're skeptical that it is. But in this case, we know what it is. So we just look at those values now that we've collected 100 of them and say, you know, funny things happen when you do simple random samples. And we got 4 that were a little farther away than we would have expected. Okay. So that's the candy machine. I already showed you or shared with you the URL. You can tinker around with this more if you want to. What I want to do is direct your attention to questions in the textbook So I'll turn this off for now and I'll come back to the video. Turn your attention to questions in the textbook on page 439, question number 27. And the question is this. Suppose the candy machine has 0.45% or 45% orange candies. In other words, a proportion of 0.45. That's the population parameter. That's truth. We know that number is accurate. How we know it, I don't know, but we know that that's truth. So that's the population parameter. And we asked the question in part A, would we be surprised if a sample of 25 had 8 orange candies in it? That's a 0.32% or a 32% proportion. Well, what would be surprising to us? Well, go back to the 2 standard deviations away. So 2 standard deviations away with 25 and a proportion of 0.45. Let me bring the calculator back up here. Let's see. So we'll recalculate that. I think you should see the calculator now. So what is the standard deviation? So square root of 0.45 times 1 minus 0.45, which is 0.55, divided by 25. That's our sample size. That gives us a standard deviation. We're going to call this 0.1. That makes it much easier. So 0.45 minus 2 times 0.1. 0.25 on the left-hand side, or the low end, 0.45 plus 2 times 0.1, 0.65 on the high end. So a proportion of 0.32 falls right in there. It falls right in there just fine, so we're not surprised by that at all. If you keep reading, how about 5 orange candies? Well, 5 orange candies corresponds to a proportion of 0.2. And 0.2 is below that 0.25 threshold. So it's more than 2 standard deviations away from the population parameter of 0.45. And so we're going to be surprised about that. We would say, wow, that's pretty unusual because it's more than 2 standard deviations away. So question B, or part B, which is more surprising, getting a sample of 25 with a proportion of 32%, or a sample of 50 in which there are 32% orange? Well, we just saw 32% orange is not surprising with a sample size of 25. To know if it would be surprising with a sample size of 50, we have to recalculate that standard deviation. So we'll calculate the square root of 0.45 times 0.55. That part doesn't change. The population parameters haven't changed. So probability of failure and success doesn't change. What has changed is sample size, n. We calculate that. That's a standard deviation of 0.07. Well, we know that the 32%, or the proportion of 0.32, is less than 0.45. So I'm just going to worry about the left-hand side of this. 0.45 minus 2 times 0.07, that's 0.31. And that's, so a proportion of 0.32 of orange candies is really close to that 2 standard deviations. So we would be much more surprised to get that value in a sample of 50 than we would a sample of 25. That's what increasing sample size, reducing variability does for us, is it draws the circle closer and closer around that mean of p hat, which we know the mean of p hat in this case is going to be 0.45. So the more samples we take, the larger the sample size, the closer those two standard deviations get to that value. And so 0.32 would be a very unusual number from there. Okay. So this is kind of a brief summary of what we talked about in class today. I'm sure I missed something that I didn't cover in class, but oh well, I forgot to, or I made a mistake saving it, so maybe this time I won't goof up so badly. I'll post this one on YouTube. I'll give you the link, and so if you weren't able to attend, or you want to go back and watch again, here we go. So we'll be in touch tomorrow. Again, we'll get together tomorrow at 1 o'clock, and we'll try again. Try to have the airport problem, part 1 and part 2, done as much as you can. I'll go through part 2 again, just to kind of walk us through it. And that'll be the focus of our call tomorrow, or our video tomorrow. So when you get a chance, if you have questions, let me know. We'll see you again tomorrow. Y'all have a good rest of the day.